we overlay this filter, 3 cross 3 filter, on this 3 cross 3 cross 24 3 cross 24 cross 24 cross image, and we keep sliding it and noting the responses. So if we do this, if we run entirely on this image, right, we end up getting 1 point here. Let's say we get the image here after running this filter. So this is just a one channel. Okay, so this is just a one channel, but typically we do this for say 64 channels or whatever, 128 channels, right? So now one channel I've explained, we got one output image. Similarly, we get another image. Assume that it is being stacked inside this thing, right? So 64 of them will be there like this. Okay, so all of this 64 times 3 cross 3 are learnable parameters. So you learn by optimizing the tasks, which can be classification, segmentation, or anything on the image, right? With the appropriate loss functions, we will learn these filters. Okay, so this is just learnable parameter that you can see. Okay, any questions on this? We can go over because this is important. I mean, you'll not end up doing this. You'll write a code, but yeah, this is important to know.
Yeah, one doubt.
Yeah, please.
Like here you have told about the number of channels per image, right? So
Right.
if it is an RGB, it will be having 3.
3, great.
And for grayscale, it will be having 1.
1, yes.
But like if in the assignment questions I have seen, like they have just told a question for an input image and they have asked for calculating the number of parameters. So how can we know whether it is an RGB or a grayscale by default if it is given like just an image, just an input image like that it have been given if it is not specified?
They haven't mentioned the size of the image.
Yeah, they have mentioned the image size.
So from there we can gauge if it is RGB or not. I mean, if they mention the channel part. So typically, right, in the deep learning, we typically mention the images as channels, cross height, cross width.
Channel cross height cross width. Okay.
Cross width, right? And if we are learning in a batch, let us say we pass batch of a data, right? So that will be a batch here. So batch cross, channels cross, height cross width. I'll explain this in Notion.
Okay, here they are given it as an input image of shape 10 10 3.
10, 10, 3.
3.
Okay, so here I think they have gone for the notation height cross width cross channels,
Okay, yeah.
right? So it's RGB.
Okay.
Right? Yeah. The typical in whatever coding we use, right, in assignments, you end up doing it is this is how you should represent, right? Channels cross height cross width. This is how the PyTorch understands.
Okay, fine.
Okay. Anything on the operation here? The this thing, convolution operation. It's clear, right?
Yeah, yes.
Okay. So I'll tell what a typical pipeline of this CNN looks like. Here we have an input image. Assume it is 3 cross some height cross width. Okay. Now we have a filters. Assume some 3 cross 3 filter, right? And here we end up getting I'll write W wherever there is a learnable this thing it's coming. And here you may notice that image size will reduce because of if we give some sprite here, right? Uh, okay, think, yeah, I think I missed having adding this thing. We add a non-linearity, typically a ReLU non-linearity, and we typically use batch normalization. Right? After W, we end up having batch norm followed by ReLU, right? That will give rise to this. Okay, so you just, the W is just an affine that we call it as affine or CNN. In the context of CNN, we just map affine to CNN. That's it. Affine, batch norm, and ReLU. This is the sequence. Right? And batch norm, ReLU, you get this thing. And there are, to reduce the size of image, there is something called as pooling operation. Okay, I'll explain what is pooling. Uh, yeah, and this keeps repeating. Okay, again W1, you get W2, and you will have same thing like batch norm. So batch norm 2, this is batch norm 1, and ReLU pooling. Like this keeps these operations keep repeating. Okay, and finally we end up getting. So one thing to note, one interesting thing to note here is, so suppose this is 3 cross 24 cross 24, 224 plus 224, right? Here, let's say in somewhere in between, the image will be 128 cross, say 32 cross 32. So what happens is this dimension goes down, height and width, and the features are accumulated across the channel dimension. So ultimately, we may end up having yeah, ultimately we may end up having a feature vector of 512 cross 1 cross 1. Right. So basically, we keep reducing the feature dimension in the spatial in the space thing, and keep accumulate learning the features across the depth, the channel dimension. Once we end up having here, and this is collapsed to a vector, 512 vector, and this is given to a classifier. This is a classifier. So if we are doing say C for 10, we'll have 10 class this thing, or C for 100, we'll have 100 outputs here. Yeah, any questions? I think I have gone a little bit fast here, but if there are any questions, I'll be happy to explain in detail.
No, it's clear.
It's clear, right? Okay, good. So one more thing to remember is this thing. If my input size is say height and width is what should I say? Say n cross n is my input image, and my filter size is f. Okay, and if I want to pad zeros and perform operations to maintain the sizes same between input and output, I can have a padding p. And there's something called a stride as well, right? Stride is how much to slide my filter on an image, right? If I slide it by one unit, its stride is 1. Slide it by 2 units, the stride is 2. Okay. Yeah, so if I apply size of filter f with these properties, right, the output size will be u n plus 2p minus f. Okay, plus 1. Height and width, because I'm assuming n to be same, this same thing carries over here. Okay, so yeah, just remember this. I mean, you may end up um, solving some problems on this. I mean, you may encounter some problems in your assignments. Uh, the other thing I wanted to explain was max pooling, right? Max pooling and average pooling. Let's say if I have 8 cross 8 image. Okay, so this is 8 cross 8, and I want to do 2 cross 2 max pooling. So what it does is it creates a 2 cross 2 grid on each of this uh, on this image. Okay, so something like this. It looks something like this. So here what we'll get is, let's say 1 2 3 4 is what are the entries. Now max pooling, what it does is the entire four pixels, it will replace it by 4. And if you have say 1 0 2 3, right, it will give 3 here. Okay, so can you guess what would be the final size here? And same thing happens on this side, right? So if we give 8 cross 8 image, right, along this we end up having 4 entries, along this we end up having 4 entries, right? So it will reduce the size on height and width to 4 cross 4. Is it clear?
Yes.
Okay, so what could be the benefits of this max pooling operation?
Mm. The output, like we get a very output dimension, image dimensions reduces.
That's great. Yes, that's a very important advantage. And uh, and there is something called as average pooling also, where each 4 cross 4 you represent by average. Okay, and yeah, so basically what it does is it makes the activations bit robust in terms of max pooling and say average pooling. Right? I mean, robust in the sense uh, the parameters are not will not be sensitive to the most of the values. I mean, which again boils down to the reduced number of dimensions, and going forward we'll use lower parameters. Right? And select distinct features into feature map. Um, I mean, if we don't do also, there will be a distinct features here into feature map. I could not follow it. So if max and min are fine, max and sorry, average pooling is fine. But let's say if we do min pooling, can you guess what could happen if I end up using ReLU activations, and if I want to use min pooling after ReLU, what could go wrong? So if you know ReLU, after applying say weights, and our activation map can contain the negative numbers as well. let's say if all the numbers are negative here, what review does is weird, right? I mean, it just knocks everything off and places zero, so you'll end up having zeros mostly, right? So that is one of the reason, main pooling can should never be used. Okay, we can go to notebook. I think this is all I wanted to give a brief overview. Fine. And if there are any questions, I can spend some more time here. Otherwise, we are good to go to notebook. Okay, so yeah, we can see the notebook, right? Can you see the notebook on my screen? I mean, you guys can speak up because I need to toggle tabs. That will be a little bit disturbing. Um, okay, so this is written in Torch code. Okay, and here we are training CIFAR 10 dataset. So CIFAR 10 dataset has 50,000 training examples, 10,000 test examples, and there are 10 classes. Okay, and here in this experiment we are making each class to be uniform, in the sense each class we pick 2,000 examples. This is done for reproducibility. And the image sizes are 32 3 cross 32 cross 32, and these are normalization values. Typically CIFAR has you can do this normalization, but CIFAR has another mean variance normalization that you can also use. And yeah, so this is how we download this EFR10 data set from the Torch Vision, which is an inbuilt library. Okay, and yeah, so this is the code to select the balanced indices for each class. So for each class, we pick 2,000 images. Right? We create a balanced data set. Given the data set, we'll create a data loader. Right? This is how we use the inbuilt Torch library to create the train loader and test loader. Okay. So coming to the first model, which is Linet, right? So here uh, we have first two con layers followed by three fully connected layers. Okay, and we apply after con, we apply ReLU. After ReLU, we do max pool with the 2 cross 2 grid, one we have discussed. After that, we again apply second con layer followed by the ReLU. Again, we do the this max pooling. Then the entire image we flatten it. Flatten it in the sense we keep this as a one vector of dimensions. I think 16 cross 5 cross 5, right? 16 times 25 basically. Then we apply three fully connected layers. Two are proper fully connected layers with the ReLU non-linearity. Again, finally, FC3 is the classifier. This is how the final outputs are done. Okay, so this represents input channels, output channels, and the filter size. Right, so because our input is 3 cross 32 cross 32, you have this. This is my input channel. and output channels are 6. So the entire filter size is 6 cross 3 cross 32 cross 32, right? And 5 is the size of filter. Clear? So this is the architecture of Linux. It basically is something like this, very simple. Okay, one CNN, another CNN. Here we get whatever we get, we flatten it. Once we flatten it, we will have 3 fully connected layers. That's it. I'm not sure. What do you mean by embedding cooling layer in it? The way we define com layer, there is no need actually. Typically, we define the weights in the initialization part, and the values and all max pools, they are not trainable. Here, whatever you have, they're all trainable parameters. Got it? Because there are no trainable parameters inside this. We can't have any trainable parameters just forward. We need to have it here. I mean, you can have it. There's nothing wrong in that, but yeah, the convention typically follow that. So if you want to have, say, batch normalization, right? You can't directly have batch normalization here. You have to have it PN1 something like that and have it here. You can write. You can write. There's nothing wrong with that. But typically, we only have the trainable parameters there. So you can write self.relu1 as nn.relu and then apply relu there. There is nothing wrong. Okay, fine. So that is Linet. Similarly, we have AlexNet. You can see all trainable parameters. Here we have 5 con layers followed by 3 fully connected layers. So this was designed for ImageNet, this thing, ImageNet challenge or initially the original AlexNet was designed for ImageNet, which has 224 cross 224 and 1000 classes and some 1 million images. That was a sort of breakthrough paper which has created which has produced very impactful results in the vision community. So this is the architecture. I mean, the same architecture, but yeah, we have more com layers and fully connected layers. Here, here they have introduced, I think, this value nonlinear, if I'm not wrong, in this work. And yeah, same thing. I mean, it's just that you have more layers, and we appropriately pass the con and reduce and cooling, and then we return the same thing. Finally fully connected. So any questions on this? Same thing with VGG. VGG came as an improvement over AlexNet. VGG came after AlexNet.
Yeah, one doubt. Can you just move a bit up?
Yeah.
So yeah, inside that like self dot convolution one, in
Huh.
that you have given 3 and 64, right? So these are the input image parameter height and width, or
No. So here, this is a there is a if you notice the filter dimensions as we described initially, it has input channels, it has a filter size which can be 5 cross 5,
Uh,
And there's something called as output channels, which can be say for 64 letters.
okay.
Okay, so if you go here, so this is my input channels. It should match with the original RGB, which is 3,
Mm.
right? And this is my output channels.
Okay.
And this is my kernel size, 3 cross 3. And this is my
Okay.
stride and padding. So if you notice, output of this con one will have 64 channels. So to match that 64 channels, the next filter should have 64 input channels, right?
Okay.
64 matches here. 192 matches here. 384 and 256 matches. Right? This one. You can see
Mm.
this, right?
Yeah. Yeah. Okay.
Okay. And the same with VGG. Right, 64 is the number of filters of, uh, yeah, you can say that, yeah, number of filters. And yeah, same thing BGG, but BGG came as an improvement over this thing. Yes. Uh, okay, so finally we create these three models, Linet, AlexNet, and BGG. And we run these models, okay, because it takes long time. I'm not running now, and we are using the Adam optimizer that's typically we use with the default learning rate of 20 minus 3, um, right? And we can see the training and validation curves here, right? So this is for Linet, which performs let's go to validation. Okay, so the Linet should have the lower performance. Ideally, VGG should have the higher performance because it is complex, and maybe we should train it more efficiently here. And then AlexNet, right? Yeah, here AlexNet gives the better metrics. Um, so you can um, train these models offline by downloading the week4 notebook, and yeah, I so this is it. I mean, this for today's notebook session. Any questions on this?
No, nothing.
Okay, then let's go to the problem sessions. Okay, I'll share the slides. Let me know if you can see the slides. Okay, you can see the question. Yes, yes, no. Can you guys see the slide? Okay, so the question is this. Okay, we ignore the biases and consider the following neural network where W is parameterized with W1 and W2. W includes W1 and W2. And you have an input X on which we apply W1, and W1 on W1 times X, right? We apply an nonlinearity G. It can be tan H. It's a typo here. Let me correct it. Okay. Tan H or ReLU anything. That's it. Right? And if we use the usual cross entropy laws, typically as we use in the classification task, and the key here is this: if we initialize the weights W1 and W2 of the neural network to zero, right, will the network will be able to learn the data? So why do you think it will not learn the data? We'll prove it now, but yeah, I just want to know the your intuition there. W1, let's call it as Z1, G, let's call it as Z2, here it is W2, let's call it as Z3. And there is a loss, error of Z3, Y. Okay, let's see. The gradients will not be computed effectively. May lead to vanishing gradient problem. No, no, no. That's not the uh, right answer. Um, anyone wants to take a chance? I mean, feel free. This is just, you can think of this as a discussion session. There's nothing to worry. But you should know this, why this thing happens. No? If no, I'll go ahead. Let's solve it. You guys want to take anything, any chance or any try? No? Okay. Um, so if what I'm saying is W1 is 0, initialized to 0, W2 is initialized to 0. What would be Z1 here? These are fully connected layers. What would be Z1? Forget about dimensions. Currently, we are not worried, let's say. Or if you want, I can put it, okay, N1 cross N2, N2 cross N3. What would be Z1? If W1 is 0, what would be Z1? X is N1 cross 1. Yes. 1 cross N, let's say. If X is 1 cross N. Great, right? The output is 0 here. This is 0. Okay. What is Z2? What is Z2? If I use Rayleigh or Tanish nonlinearity, at 0, what would be Z2?
1.
No. So Tanish is something like this, right?
Yes.
At 0, it outputs 0. And if you use Rayleigh, it is again 0, right? At 0, it would be 0. But even the
If
Z2 is
we
also
use sigmoid,
sigma, it will be 0.5.
0.5. Okay.
Right? Sigma, it will be 0.5. So Z2 is 0. Now, I'm saying Z2 is 0. Now, WT is also 0. What is Z3? There is no bias. Right? Z3 is also 0. Okay. And now I'm taking 0 vector here and I'm computing some loss y. Say some softmax is applied on this 0 vector. We get, let's say, 10 class problem. If I do softmax of Z3, what will we get for a 10 class problem? What is softmax? E power z by summation of e power z, right? So since all are same, softmax will just throw out 1 by 10, 1 by 10, 1 by 10. If it is a 10 class problem, right? It exponentiates and normalizes. And we get some non-zero loss here, some loss function. I mean, can you speak? Uh, that's better because it's quite disturbing. I need to keep toggle here and there. Okay. Right. So let's say we got. Um, Let me adjust my this thing dimensions here into cross n1 just for my notational convenience. And this is n3 cross n2. The reason I'm saying is I want to have n1 cross 1. I want to write something like this. Z1 is equal to W1 times X1. X basically W1 into X. And Z2 is G of Z1 and Z3 is W2 times Z2. Okay, that's all. This is all we care about. And there is a loss function L which is doing softmax on Z3. I'm just calling it as Z3 comma y. And let's say we got some gradient with respect to Z3. Okay, and this will be of height. The dimension of this would be the dimension of Z3, which is N3. Okay, so this will be of N3 cross 1. Right. I have a gradient of loss with respect to Z3. I want to find the gradient of W2, right? What could be the this thing? What should I do? So by following the chain rule, I should have gradient of loss. Gradient of Z3 with respect to W2. Okay. And remember W2 dimension is N3 cross N2, right? It belongs to N3 cross N2, right? So here this thing will translate to this thing, gradient of L with respect to Z3 times Z3 with respect to W2. If you do, we end up getting Z2 transpose. Okay. So this is N3 cross 1 and this is 1 cross N2. Right? If you multiply, we get N3 cross N2 like this. So now we got gradient with respect to W2, gradient of loss with respect to W2, right? Which can be defined like this by chain rule, which ended up becoming this. Now, what was Z2 in the forward pass? Yeah, what was Z2 in the forward pass? Z2 here. If Z2 is 0, right? That's it. If you put Z2 0 here, then that's it. You get 0 matrix. Okay. Any questions on this? Yes. No. Any questions on this? Okay. Anyone followed, right? Why it is zero? Okay. Um, yeah, I get a response only from one. I mean, what about others? I can spend some time.
It's clear.
Good. And yeah, what do we need here, right? Another thing I asked was what would be the gradient of loss with respect to W1. Now, for that we need gradient of loss with respect to Z1. Okay, so let's do that because we know the gradient of loss with respect to Z2. We know we can compute, right? Gradient of loss with respect to Z2. Um, I think I have that in the slides. Okay, yeah, we need the. Sorry, what was that? This is W1. We need the gradient of loss with respect to W1. I think W2 is zero. We need this. For that, we need gradient of loss with respect to Z1. And for that, we have to get the gradient of loss with respect to Z2 and gradient of loss with respect to of Z2 with respect to Z1 due to chain because of chain theory. But if you see the gradient of loss with respect to Z2, of loss with respect to Z2 is W2 transpose times gradient of loss with respect to Z3. Now, because W2 was zero, right, and this will be zero, right, and because this is zero, gradient of loss with respect to Z1 will be zero. Okay, and because gradient of loss with respect to Z1 is zero, gradient of loss with respect to W1 will be zero because of this. So finally, we end up in such a situation that we are not, no matter what we do, we are not coming out of this zero update, right? So the same is true if you have biases and biases are initialized to zero. But this is not true when the biases are non-zero. Okay. So learning will pick up after some time if biases are non-zero. Fine. Fine. Can go to next question. Okay. Next question is also similar thing but of a different flavor. The same network, what we now do is we initialize all the weights of W1 to same number, same real number. So W1 and W2 to same real number. What do you think the network will do? Same thing, we don't have biases here as well. So why do you think it will not run? As they will be constant gradients. They're partly correct. So what happens is in this case, um, what happens in this case is uh, if all the matrices have the same weights, right? Our neurons, right, will behave in the same way. All the neurons will mimic each other. You got it. right? Say, let me go to this thing. This is my X and this is my weight matrix W1, and let's say this is Z1. Okay, if all the values of W1 are say 1.5, right? So what would it do to this input, right? It just sums up all the values of my input x1 to say xd, right? So 10 x10 whatever, right? It just sums and scales it by 1.5. So all the neurons that are coming here behave in the same way, right? And when you do an update, back propagation update, all the neurons will update by the same amount, right? So effectively we are training a single neuron, that's it, nothing more than that. And basically what's happening is the data whatever we have x1 to say xd, we just effectively we are just summing up all the data x1 plus x2 plus xd, and we are running a single one dimension neural network with some nonlinearity, that's it. Okay, so that's why it will not learn that this is the reason why it will not learn. Gradients are not constant, gradients are evolving, but it is as good as just summing up the features and learning on them, that's it. Clear? I can explain it again if there is a question, if there are doubts, because you should know these things. I mean, after doing this course you should know these things. This is called as symmetry breaking in neural networks. So you should never initialize all the weights to same value and never initialize them to zeros. Network will not learn. Questions? No questions? No questions, I'll move ahead. Okay, then I'm assuming things are clear. I'm going ahead. Okay, so why CNNs are better than fully connected neural networks for image data, right? The option is it's parameter efficient compared to fully connected neural networks. CNNs by design have inductive biases per image, and one and two are correct. Only one is correct. Only two is correct. What do you think? Okay, let me flash the question. Then you guys can type in the answer. Only one is correct. No, two is correct. The key reason for using CNNs is to provide the image inductive bias, right? I mean, the translation invariance property, which I which I discussed in the first part of the today's lecture. Okay. Um, Now, I think maybe you guys should be able to answer this. We have an input image of size 3 cross 64 cross 64, channel height width. So ideally, when someone asks questions, right, they should clearly specify this. Otherwise, it's a little confusing, right? And now we have a filter of size 3 cross 5 cross 5, and the number of filters used are 3. If stride is of 2 and zero padding are used, what would be the size of our filter? Based on what initially I have written down, you should be able to solve this. Um, Output filter size, I mean, this is quite a size of output activation, right? Size of the output, maybe, yeah. This is fine. Yeah. After applying the filter, what is the output size? 3 cross 30 cross 30 only, is that the true answer? No, no, no. Yeah, I think you're right. You guys are right. Yeah. Sorry. Sorry. The number of filters which are three. Fine. Yeah. Okay. Fine. What are the key benefits of pooling layer in CNN?
Sir, what is the last question answer?
It's 3 cross 30 cross 30. Just apply this formula. That's it. Okay. Yeah. What do you think is the benefits of pooling layer of CNN? Option 4. Yeah. So all of these are true, right? All these are. It reduces parameters that in turn benefits compute, and it also has some impact to the little bit of translation ingredients, right? And yeah, finally, I mean, I gave the answer here. So, what kind of features that the shallow layers and deeper layers of CNN captures? Right? Basically, in the initial part of the CNNs, right, it captures the features such as edges and right? And deep inside the CNNs, it depending upon your task, it captures the high level features such as the objects, right, within the image. If you classify and say cats and dogs, it encapsulates the entire information of that content in the image, basically. Okay. So this is how the learning happens. So it's a low level features to entire the this thing, image in CNNs. Okay, so this is all I had for you today. If there are any questions, we can I can go over. Otherwise, we can stop the our session for today.
Sir, is it possible to discuss an assignment question here?
The current assignment, no, but I think previous maybe I can attempt to solve it.
No, actually, this current assignment question.
I was facing problem with lost dot backward. What was the problem? Can you paste that error here? Um, can you paste here and let me take a look at it now if you have it. Okay, let's wait for a minute. So yeah, what do you guys prefer the timing? So is 4 to 6 okay, or 5 to 7?
Uh,
Can we have it to avoid clash with the other thing?
Actually, this particular session, the problem solving session, will be on weekends.
Yeah, Saturday, Sunday. Yeah. You want on weekdays? You guys want on weekday? That would be little difficult for me.
No, 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 no. I was just asking.
Yeah. So the lost or backward throwing. Okay, this error is this thing, right? I mean, it's quite common. Um, so in the notebook, if you are running it right, I suggest uh, you run cleaning up the entire this thing. You will not face. So basically, what can happen is, say you ran 2 forward passes and you do a backward, or you do one forward pass with couple of lost or backwards. It may end up having this. I suggest you clean the notebook. I mean, just clean up all the history and the variables, and then it should work. I don't know about the forum, but this is quite a common error. Um, okay, and that should be fixed if you reset your notebook and run it. It should be fixed. Yeah, I mean you just need to reset this thing and the notebook, clean up the history, and it will work. I'm pretty sure it will. Okay. Okay, so let's meet next week. For next week, we will be discussing the architectures, probably mostly the resonates and the other stuff. Okay. So maybe 4 to 6 is convenient. I'll stick to this time then. Okay, see you next week. Bye.
Thank you.